have you ever stopped just for a second to think about what's really happening when you tap an app or click a link?
Yeah.
And boom, the website just appears.
Yeah, I mean, the server for that site, it could be just down the road, or it could be thousands of miles away, maybe at your company's main office.
It really does feel like magic sometimes, doesn't it? This seamless global connection, like your data just beams across the planet instantly.
It does feel like that.
But of course, it's not magic.
Yeah.
Not at all. It's incredibly sophisticated engineering. So today, we're pulling back the curtain on that, well, invisible infrastructure. We're doing a deep dive into wide area networks, WANs, and the absolutely fundamental world of IP routing. This is really the hidden machinery behind almost everything we do online.
It's pretty fascinating because these core parts of networking, they work together so smoothly that honestly, most of us never give them a second thought.
Right.
Our main source for this, Fundamentals of WANs and IP Routing, it's a great guide for this. And, while WANs often get talked about as just one piece of the puzzle, really getting your head around how IP routing works, really works, you need a solid grasp of these long-distance connections first. They're foundational.
That makes sense. So our mission today really is to equip you with the core ideas. How data actually travels these huge distances, connecting remote places, and how the Internet Protocol, IP, acts like the master conductor.
The traffic cop.
Exactly. Making that whole journey efficient and reliable. So get ready for maybe some surprising facts and hopefully a few aha moments that might just change how you see your everyday internet use.
Definitely.
Okay, let's start our journey with those invisible bridges, wide area networks, or WANs. So at the most basic level, a WAN connects local networks, LANs that are geographically separate.
Right. We're talking anything from, a few miles apart to hundreds, maybe even thousands of miles. They're essentially the long-haul superhighways for your digital information.
The superhighways, I like that.
Yeah, and these WAN technologies, they're responsible for defining the physical stuff that's layer 1 in the OSI model and the data link protocols, which is layer 2.
Okay, these are the underlying rules, the standards that define how the raw bits, the ones and zeros, actually get moved from one distant point to another. Without them, well, our data literally has no road to travel on. And these roads, they haven't just appeared overnight, right? They've evolved quite a bit.
Oh, absolutely.
Our sources highlight two really key types that show that evolution, the historically important leased line WANs, and then the much more modern, kind of everywhere now, Ethernet WAN.
Exactly. Two major milestones.
So to really appreciate where we are now, it probably helps to see where we started. Let's rewind a bit, maybe back to the 1960s. What was the tech that first let businesses connect offices miles apart?
That's a great starting point, yeah, because it really sets the stage. In those early days, companies used what were called leased line WANs.
Oh, leased lines, okay.
Imagine your company has, say, an office in New York and another one in London. You typically put a router in each office, hook it up to the local network there, and then you'd literally lease a dedicated line from a service provider, usually at telco, a phone company back then, to link those two routers together.
Right. I've seen those diagrams with the sort of crooked line, the lightning bolt symbol between routers.
That's the one. That's the classic symbol for a leased line. It visually represents that dedicated long-distance connection.
Okay, dedicated line. What does that actually mean physically? Is it like one super long cable stretching across the Atlantic?
Well, conceptually, it acts like a direct, full duplex Ethernet link between the two routers. It uses two pairs of wires, one for sending, one for receiving, so data can flow both ways at the same time.
Okay.
But yeah, to clarify, it's definitely not one single cable running from building A to building B across continents. No, it's actually the telco's huge, very complex network.
Right.
With things called central offices or COs and all sorts of internal switches working behind the scenes. They create the appearance, the effect of that direct, dedicated connection just for your data.
Interesting. And our source points out there are tons of different names for these leased lines, like leased circuit, serial link, point-to-point link, private line, even specific ones like T1. Why so many names for what seems like the same thing?
That's a really good observation. It's because while they all generally mean a dedicated point-to-point connection, the different terms often highlight specific technical details or maybe the historical context. Like T1, that specifically means a North American digital line running at exactly 1.544 megabits per second. Very precise.
Right.
Serial link just describes how the bits are sent one after another. Private line emphasizes that it's just for you, not shared. So each name adds a little nuance to that core idea of a leased dedicated circuit.
Makes sense.
Now, these leased lines provide the physical connection, layer 1, but routers still need layer 2 protocols to manage the data flow over that line.
Right.
Two big ones for leased lines were HDLC, that's high-level data link control, from the 70s, and PPP, the point-to-point protocol, which came later in the 90s and had more features.
Okay, HDLC and PPP.
And the neat thing about these point-to-point links is their simplicity. When one router sends, say, an HDLC frame, there's only one place it can possibly go: the router at the other end of that dedicated wire.
Yeah. No confusion.
Exactly. Our source has a fun analogy for this. It says, it's sort of like when you have lunch with your friend Gary, and only Gary. You don't need to start every sentence with, "Hey, Gary." He knows you are talking to him.
Huh. I like that. So the destination is implied.
Precisely. So while HDLC technically has an address field in its header, the actual value isn't that critical because, well, where else could it go? These protocols also do important stuff like error checking using a frame check sequence or FCS field, kind of like Ethernet.
Okay.
But they're much simpler overall because of that strictly point-to-point nature.
So if we were to sum up the lease line era, they were simple from the customer's view, pretty reliable, private, and available almost everywhere back then.
True.
But those pros came with some pretty big cons, right? Especially as things started speeding up digitally.
Absolutely. By today's standards, their weaknesses became really obvious. They were relatively slow. You were lucky to get speeds in the tens of megabits per second.
Wow, that's slow now.
Right. And they were incredibly expensive. Plus, getting one installed could take ages, sometimes months. So all these factors together, they create a huge pressure for something better. Faster, cheaper, more flexible.
Yeah, those limitations, especially the cost and the speed bottleneck of leased lines, they must have become huge problems as our need for data just exploded.
Exactly right. They were roadblocks.
So how did the industry move on? How did we get from those dedicated but kind of slow connections to something that can handle the modern internet?
Well, the demand for something better was definitely there. And maybe surprisingly, the answer came from a technology we already used heavily in our local networks: Ethernet.
Ethernet. But wasn't that just for short distances, like inside a building?
It was, for decades. Strictly limited to LANs because of cable length issues, often just a kilometer or two, maybe. But the IE, that's the Institute of Electrical and Electronics Engineers, they kept working on it.
Ah, the standards body.
Yep. They steadily improved Ethernet standards, pushing its reach dramatically further. We're talking tens, even hundreds of kilometers eventually, using single-mode fiber optic cables. Things like 1,000 base LX for 5 kilometers or 1,000 base ZX for up to 70 kilometers. Suddenly, Ethernet wasn't just for LANs anymore. It became a really viable, powerful WAN technology.
Okay, so today that means service providers, SPs, they offer different kinds of Ethernet WAN services.
Exactly. Companies connect their routers, usually via a fiber Ethernet link, to the SP's network. Typically, this connects to a nearby point of presence or POP.
POP. Got it. The SP's local hub.
Right. And what's really key for the customer is that logically it behaves just like a simple point-to-point connection between their two routers, very much like the old leased line concept.
Even though physically it's plugging into this big provider network.
Precisely. Even though physically, yeah, your router connects into the SP's much larger, more complex network, you might hear these called Ethernet WAN or Ethernet point-to-point link, maybe E-line, or sometimes EMPLS.
EMPLS.
Yeah, Ethernet over MPLS,
Okay.
a multi-protocol label switching. It's one of the underlying technologies providers use. But the point is, the underlying tech might be sophisticated, but for the user, it's designed to feel simple, like that direct connection.
Okay, so now we've got these powerful WAN links set up, connecting our distant offices or data centers. Great. But the big question is, how does data actually get from point A to point B, making sure it finds the right destination across potentially lots of different networks?
Right, that's the core problem.
And this is where IP routing steps onto the stage. It's the central conductor, really orchestrating that whole journey.
That's a perfect way to put it. The Internet Protocol, IP, and our sources focus on IPv4 mostly deals entirely with the logical details, getting packets from the original source computer all the way to the final destination computer.
Logical, not physical.
Exactly. IP doesn't worry about how the bits physically move. It relies on those lower layers we just talked about, the LANs and the WANs, to do the actual, heavy lifting of transmitting signals. IP's job is purely directional, knowing where to send the packet next.
So let's walk through that journey. Say my computer, PC1, wants to send data to PC2, and they're separated by, I don't know, a few routers.
Okay.
First, PC1 uses what our source calls host forwarding logic. Right. It looks at PC2's IP address and realizes, hey, that's not on my local network. So PC1's logic says, okay, I need to send this packet to my default router or default gateway. That's the router on my own LAN whose job it is to handle traffic going elsewhere.
Precisely. And that's where router forwarding logic takes over. Every router follows this basic process. They maintain an IP routing table.
A roadmap.
Kind of like a set of freeway signs for data, yeah. When a packet arrives, the router looks at the packet's destination IP address. It matches that address to an entry in its table. And that table entry tells the router exactly where to send the packet next. Maybe it's another router further down the path, or maybe it's the final destination host itself if it's directly connected.
What if there's more than one way to get there?
Good question. If there are multiple paths, routers use something called a metric. It's basically a calculated value that represents the cost or preference for a route.
Like how good the route is.
Exactly. Maybe based on speed or reliability or hop count. The router uses the metric to choose the best path according to its configuration.
Okay, so this packet is hopping from router to router, potentially crossing different kinds of links, Ethernet LANs, maybe an Ethernet WAN, maybe even an older link type somewhere. What happens to the packet itself? Does it keep getting changed?
This is the crucial point. The dance between the network layer, IP, and the data link layer, it's really clever.
How so?
Well, think about separation of concerns. IP, the network layer, has a big picture view. Get this packet towards the final destination IP address. The data link layer, layer 2, handles the specifics for each individual hop. Okay, I need to wrap this IP packet in the right kind of frame, maybe an Ethernet frame, maybe an HDLC frame, and send it across this specific link to the next device.
So it repackages it at each step.
Exactly. Here's the process, step by step at each router. 1, the router receives a data link frame, like an Ethernet frame. 2, it checks for errors using that FCS field. 3, assuming it's okay, it strips off and discards the old data link header and trailer. Gone. What's left is just the original IP packet.
Okay, just the IP packet now.
4, the router looks at the destination IP address inside that packet and consults its routing table to decide the next hop. 5, then, and this is key, it takes that original IP packet and encapsulates it inside a brand new data link header and trailer. This new wrapper is specifically formatted for the outgoing link technology. So if the next hop is Ethernet, it gets a new Ethernet header and trailer. If it's something else, it gets the appropriate wrapper for that. 6, finally, it sends the new frame out the correct interface.
Wow, so the data link stuff is constantly changing, hop by hop.
Constantly changing. And this is the fundamental aha moment our source emphasizes. If you connect this to the bigger picture, notice that the original IP header, the one with the ultimate source and destination IP addresses, it remains completely untouched, completely unchanged throughout that entire journey, from the moment it leaves PC1 until it arrives at PC2. Only the layer 2 envelopes, the data link headers and trailers, are added and removed at each hop.
That's amazing. The core letter stays the same, just gets put in different envelopes at each post office.
Perfect analogy. That's exactly it.
Okay, that makes sense. Now, how does the way we structure IP addresses themselves help make all this routing efficient?
Another clever part of the design. IP addresses, as you know, identify specific network interfaces, like a postal address for a device.
Right.
But TCP/IP also groups these addresses into IP networks, or more commonly, IP subnets. Think of these as collections of IP addresses that are all on the same physical network segment.
Like a neighborhood or a ZIP code.
Exactly like a ZIP code. It's a group of addresses in the same logical area. And this grouping leads to 2 really fundamental rules in network design, according to our source.
Okay, what are they?
Rule 1. Any 2 IP addresses that are not separated by a router must belong to the same IP subnet. They have to be in the same ZIP code.
Makes sense. They're neighbors.
Rule 2. Conversely, any 2 IP addresses that are separated by at least one router must belong to different IP subnets, different ZIP codes.
Okay, so routers always sit between subnets.
Precisely. And the huge benefit of this, think about the routing tables again.
They don't need an entry for every single house number, just for the ZIP code.
You got it. Routers can have one single entry in their table that represents an entire subnet, a whole group of addresses. Instead of needing millions of entries for individual hosts, they need far fewer entries for entire networks or subnets. This makes routing tables much, much smaller, and the whole lookup process way more efficient and scalable.
That's incredibly efficient.
It really is. It's key to how the internet scales. And just as a quick detail, remember that IPv4 header we talked about? It's typically 20 bytes. Inside are the 32-bit source IP and the 32-bit destination IP. And again, those two addresses, they stay constant end-to-end, guiding the packet across the whole internetwork.
Okay, so we have the links, we have the IP logic guiding packets using addresses and subnets, but sending packets requires more than just knowing where to go eventually. Routers need to actually learn about all the possible routes, right?
Yeah.
Especially when networks change.
Absolutely. They need dynamic information. This is where our support crew of essential network protocols really comes into play.
The support crew.
Yeah.
Oh.
First up are the IP routing protocols themselves.
Right.
Their whole job is to let routers automatically discover and learn the paths, the routes to all the different IP networks and subnets out there.
How do they do that generally?
Our source breaks it down into about 3 general steps. First, every router automatically knows the routes for the subnets it's directly connected to, its own local neighborhoods.
Okay, that's step 1.
Second, the routing protocol running on the router sends out routing update messages to its neighboring routers. It's basically saying, hey neighbors, here are the networks I know how to reach.
Sharing information.
Exactly. And third, routers listen to these updates from their neighbors. They learn about new routes, they add them to their routing table, and they figure out which neighbor is the best next hop router to reach that destination network.
Like passing directions along.
Kind of, yeah. Our source uses an example. Maybe router R3 learns about network 150.150.4.0 because it's directly connected. R3 tells R2 about it. R2 learns the route via R3 and adds it to its table. Then R2 tells R1. Now R1 knows it can reach 150.150.4.0 by sending packets to R2. The information propagates. And remember that metric. Routing protocols use metrics to choose the best path if they learn multiple ways to reach the same network.
Got it. Okay, but thinking about all those IP addresses, 150.150.4.0, we humans aren't great with long strings of numbers. We like names, like google.com.
You're absolutely right. That's a huge usability issue, and that's why we have the domain name system, or DNS. It's indispensable.
Right. Resolves names to numbers.
Exactly. The problem is users prefer host names, like google.com, over those numerical IP addresses, like, 64.233.177.110, whatever it is.
Right.
DNS solves this beautifully.
How does it work, basically?
When your computer needs to connect to, say, google.com, it sends a DNS query message to a DNS server. It's basically asking, what's the IP address for google.com? The DNS server looks it up and sends back a DNS reply containing the corresponding IP address. Your computer then takes that IP address and uses it to actually send the packet to Google's server.
So it's like a giant phone book for the internet.
A massive, distributed, worldwide phone book. That's a key point. No single DNS server knows everything. They all work together. If one server doesn't know the answer, it forwards the query to another server that might, until eventually the authoritative answer is found and sent back to your computer.
Clever. Okay, so we have the name resolved to an IP. But wait, even with the IP address, how does a router, or even my computer, know the physical address, like the MAC address on Ethernet, to actually send the frame on the local network? IP is logical, but the frame needs that physical address for the specific wire, right?
Excellent point. You've hit on the need for the Address Resolution Protocol, or ARP.
ARP.
The exact problem ARP solves is this. On a local network, like your home Ethernet or Wi-Fi, your device might know a neighbor's IP address, like your default router's IP, but it doesn't initially know its layer 2 physical MAC address, and it needs that MAC address to build the Ethernet frame correctly.
Right, the envelope needs the local street address.
Perfect. So when your device needs to send an IP packet to a neighbor on the same LAN, it first sends out an ARP request. This is a broadcast message sent to everyone on the local network, basically shouting, hey, who has IP address 192.168.1.1? If that's you, please tell me your MMASH address.
Okay, it broadcasts the question.
The device that has that IP address, in this case the router, sees the request and sends back a targeted ARP reply directly to the original asker saying, yep, that's me. My M address is whatever the M is.
So it gets the answer directly.
Right. And then to avoid doing this constantly, devices store these IP to MAC mappings they learn in an ARP cache, like a little temporary memory.
Right.
So next time it needs to send to that IP, it just looks in its cache first.
Candy, can you actually see that cache?
You can. On most computers, you can open a command prompt or terminal and type something like RPA, and it'll show you the IP and ME addresses your computer currently knows about on the local network.
Cool. Okay, last piece of the puzzle then. We've got names resolved, routes learned, local addresses found, all these layers working. How do we actually test if basic communication is even possible, how do we check if packets can actually get from A to B?
For that fundamental test, we use ping and the underlying protocol, ICMP, which stands for Internet Control Message Protocol.
Ping. I've definitely used that.
Most people who've done any network troubleshooting have. Ping is essentially a utility that sends a special type of ICMP message called an ICMP echo request to a target IP address.
Cool.
If the target device receives the echo request and is working correctly at the network layer, it's designed to reply with an ICMP echo reply message back to the sender.
So it's like sending a sonar pulse and waiting for the echo.
Exactly like that. And why ping is so fundamental is that it tests the core connectivity layers 1, 2, and 3. It checks if the physical link works, if the data link framing works, and if basic IP routing between the 2 points works, all without needing any specific application like a web server to be running on the other end. It just confirms, can my packets reach you and can yours reach me? It's often the very first step in diagnosing any network problem.
Wow. Okay. We have covered a lot of ground today. It's quite the journey we traced.
It really is.
From those foundational physical WAN links, leased lines, Ethernet WANs, connecting distant places, through the really clever logical routing decisions made by IP, with all that encapsulation and de-encapsulation happening constantly,
Hop, hop.
all the way to that essential support crew, the routing protocol, sharing roadmaps, DNS translating names, ARP finding local addresses, and ping just checking if the lights are on. We've really seen the invisible highways, the sophisticated navigation systems, and the communication tools that power our whole interconnected world. And it's all happening in, milliseconds every time you stream a video or send a message?
And if you sort of zoom out for a second, connect it all to the bigger picture,
Yeah.
it truly highlights how many different layers of abstraction and specialized protocols have to work together just seamlessly to get even a single packet of data from one corner of the globe to another.
It's pretty incredible.
It's this intricate dance, really, between hardware and software. Every piece has its specific job, all contributing to making our global networks work as reliably and efficiently as they mostly do.
So as we wrap up thinking about WANs again,
Yeah.
especially remembering that private line idea from the old leased lines, it does raise an interesting question for you, our listener, to think about. In today's world, with these highly virtualized, often shared Ethernet WAN environments, where lots of different customers' data might be flowing through the same provider infrastructure, how does this invisible network architecture we've discussed inherently shape the ongoing and really important conversations we have about data privacy and network security? Something to ponder.
Definitely something to think about.
Well, thank you so much for joining us on this deep dive into the truly fascinating world of WANs and IP routing. We hope you feel a little more clued in now and maybe, just maybe, a little less like your data is simply teleporting around the world by magic.